Hello, everybody. So what we're going to be looking at today is section 3.4 in your book, which is going to be motion in space. Basically, we're going to cover two topics here. We're going to cover the velocity and acceleration vectors for a particle moving in space. This is going to be a lot like velocity and acceleration that you did in, a calculus 1 class, right? Like the derivative of position is velocity and the derivative of velocity is acceleration. So this part here is going to be relatively straightforward, although some of the problems are going to be, kind of a little bit longer calculations for like finding something like, where is a particle speed maximum or minimum, that kind of thing. But still, conceptually pretty straightforward. The other thing we're going to be doing is we're going to be talking about the tangential and normal components of acceleration. And what this is going to be doing is we're going to be breaking apart the acceleration vector into two pieces. One that's parallel to the curve and then, or parallel to the tangent of the curve, which is the same thing, and one that's 90 degrees away. Of course, we will, actually explain what that means when we get to that concept. So let's go ahead and talk about these. We'll start with velocity and acceleration. So let's go. So here's our definition here. So we need r of t vector is going to be twice differentiable. Twice differentiable because first derivative is going to be velocity, second derivative is going to be acceleration. And so we want to make sure that we can actually find those. And so that's why it will have to be twice differentiable, vector valued function. And so hold on. Vector valued function of t, where t represents time. Time, and r of t represents the position at that time. Okay, so that's just the straightforward definition of a particle that's moving, right? We have an object moving, and t is time, and r of t is its position. So what we're going to do then is we're going to define these functions. So velocity, the velocity function here, is going to be v of t. We'll write that as a vector v of t. And the way you calculate it is simply with the derivative of the position function. So velocity is the derivative of position. Right? Just like calculus 1. Then we're going to define the acceleration vector. I should actually maybe back this up here so I can call it velocity vector. And the acceleration vector is going to be a of t, again with the vector, so there's a vector symbol over it. So that's going to be the derivative of velocity. And the derivative of velocity is going to be the second derivative of position, right? So the derivative of the derivative of the position. Okay, so acceleration is the derivative of velocity. That again matches what you know from calculus 1. Now, speed is not a vector. So the speed, this is a scalar quantity, not a vector, is given by, and you know that in calculus 1, when you want the speed of an object, what you do is you just take the absolute value of velocity, right? Like if velocity is 3, then your speed is 3. If your velocity is negative 3, your speed is still 3, right? Because the negative indicates direction of travel. Same thing has to happen here, but because these are vectors, you want to know how fast something is going, you actually have to take the magnitude of the vector. So the speed is going to be given by this. Speed equals, now I'm going to write this the way they do. They write v of t, which you might think like, oh, we already used v of t, but this is v of t with no vector symbol. So this is actually a different variable than this one, because this one's not a vector. So they use just v of t, and that's going to be the magnitude of the vector v, like that, or the magnitude of r prime. And yeah, that's about it. So yeah, so those are our basic definitions here. Okay, and I'm not going to write down the formulas for these because we already know how to do derivatives, and we can just get started here. So let's see. Example. Oh, actually, I do want to draw a picture before we do this. So so suppose we have like a car, right? So I don't know how to draw a car. So there's my car, there's the windshield, there's a back windshield, there's a tire, there's a tire, there's a tire, there's a tire. It looks like a skateboard. But anyway, and suppose it's going like on a road here. I'm not going to draw the road. I'm going to draw the path that it travels along. Like that. Okay. Actually, hold on a second. I want to erase that. I realized I drew that in a bad place. I'm going to, oh, there's no way I could do that. Oh, well. Okay, so let's say we have the car do this. Trying to make it curve here. Okay, that should be good. Okay, so let's say that that's a car moving along a curve. Okay, and I should get rid of that. So it's going in the direction, this direction. Okay, now when you do this, you're going to find the velocity vector and you're going to find the acceleration vector. So the velocity vector is going to end up pointing like in a direction like this, which is going to be, you know, tangent to the curve. So v of t will be tangent to the curve. Okay, now the acceleration vector, which we didn't draw here, is going to be like pointing basically, not basically, it'll be pointing to the inside of a curve. So like if this is making a turn, then the acceleration vector points to the inside of the turn. So that's going to be the typical case. So like a of t is going to look something like that. And this would be like v of t. Right? So they're not at right angles or anything. Typically, this is just going to be points kind of forward and inside. Often. Okay, so that's kind of where they are if you were going to plot them on a graph. But, you know, we can see it for a specific example. So let's do an example. So let's say, where's my example? Okay, so a particle moves along a parabolic path given by, and we got a curve here. So r of t, and this is going to be a two-component vector here. It's t squared I plus square root 5 minus t squared j, and t is measured in seconds, okay? They don't say what the position is measured in, but t is measuring seconds. Okay, now what they want is they say, find the velocity, acceleration, and speed as functions of time. Okay, and B is sketch the curve along with the velocity vector at time t equals 1. Actually, as soon as I'm writing this down, what I'm realizing is that I actually want to change this problem. So we're going to switch out this problem for a book problem. We're not shopping for watches. That's not what we're doing. Amazon is wrong. Let me log in here to our homework. We are Math 4C. There we are. We are section 3.4. Okay, so I'm stealing a function from here because I want to show you how to plot it, like how to solve the problem the way they ask it, which is a little bit different. So let's cheat, submit. Trying to get to a graphing problem is what I'm doing here. Yeah, that's what I want. Okay, so we're going to use this function actually instead of ours. That way we can plot it on that curve. So this function is just t squared I, and then this one is 4t minus 1j. Okay, now they wrote it in the alternate form there, but we have this. Okay, so let's go ahead and do this. So we're going to start with part A, of course, which is going to be find, what is it? Velocity, acceleration, and speed, right? Yeah. Okay, so we start out with the r that we're given, and the r that we're given is t squared. I'll write it in this form, t squared, comma, 4t minus 1. Okay, so if you're trying to find the v of t, then we're just going to find the derivative, right? So this is velocity, and we just want the derivative of position. I feel like I didn't write the word velocity there. So we know that it's just the derivative of position. So we just take the derivative of this function with respect to t. So the derivative of t squared is 2t. The derivative of 4t minus 1 is 4. Okay. And then we have acceleration, a of t. And we know that the acceleration is going to be the derivative of velocity. So it's v prime of t. So we're going to take the derivative of this one. So the derivative here, the derivative of 2t with respect to t is 2. The derivative of 4 with respect to t is 0. So simple acceleration vector. And then we got speed. And so the way you calculate speed, they use v of t with no vector symbol, and it is the magnitude of the velocity vector. So it's the magnitude of 2t comma 4, like that. So you work that out. So it's going to be a square root of 2t squared plus 4 squared. So we get, so v of t is simply going to be square root 4t squared plus 16. And you can simplify that if you want, but I'm not. So we got a speed there. We've got our acceleration here, and then we got our velocity here. So velocity, acceleration, and speed are not that hard to do. Just two derivatives and then a magnitude. Okay, now they say sketch the curve along with the velocity vector at time t equals 1. Okay, so what you would have to do here if you were going to do this purely by hand is first we would need the plot of function. Okay, so to get a plot of the function, there's not really going to be a shortcut, if you're doing this purely by hand. you would just have to make like a table of values or something and go like, come on, t r of t. See if you can figure it out. So if we just go like 0, 1, 2, 3, 4, and then we can plug those into the original r, which, oh, I can see it right there. So r is right here. So if you plug in 0, you're going to get 0, comma, -1, right? And if you put a 1 into that function, you're going to get 1, comma, 4 times 1 is 4 minus 1 is 3. If you put a 2 in there, you're going to get 2 squared is 4, and then 14 minus 1. 4 times 2 is 8, 8 minus 1 is 7. And probably this is going to be the last one that I do. If you put a 3 in there, 3 squared is 9, and then if you put 3 in the other one, 3 times 4 is 12, 12 minus 1 is 11. Okay, so we're just going to plot that many points. Okay, so I made a little table of values. We calculated those from the function, and then if we go to actually plot this on a 2D plane, looks like they're all positive. How far do we want to go? So in the x direction, we might need to go out to 10 maybe. I'm going to go 2, 4, 6, 8, 10. And then in the y direction, even further. So 2, 4, 6, 8, 10, 12. And even to -2, right? There's some negatives. Okay, so if you go to plot this curve here, then at time 0, you are at, the vector is 0, -1. But you plot that as a position, right? I know it's a vector, but you plot it at the point 0, -1. So near 0, -1 is right here. And that's the t equals 0 point. And then you're at 1, 3. 1, 3 is here. So that's the t equals 1 point. Then you're at 4, 7. So 4, 7. 4, 7 is right here. Like that. And then 9, 11. 9, 11 is right here. Okay. So this is your curve. Like that. Okay. Now you don't have to do that on the computer. Okay. But on this one, I'm going to go to the computer in a minute, but I'm plotting this one by hand. Now on this graph, what I want to do is I also want to plot, I said plot the function, but I want to plot the function along with the velocity vector at time t equals 1. So t equals 1, first of all, you have to find it. So you would need to know where t equals 1 is. So like r, oops, so you would need to know r of 1 first in order to get that plotted in the right place. So we calculated it and it was 1, 3. Now you also need to know the velocity vector at 1, and we need to know the acceleration vector at 1. Actually, I didn't say to plot the acceleration, but I will. So how do I get velocity at time 1? Right, you got to go up to the velocity equation and you're going to plug in a 1 here. So if you plug a 1 in here, you're going to get 2 times 1, 4. So 2, 4. Okay, and then a of 1. So a of 1 is plugging a 1 into the acceleration vector. The acceleration vector is here. There's no t's, so it's just going to be 2, 0. Okay, and I'm going to say we're going to plot v of t and actually v of 1 and v of 1 and a of 1. Just because this is what you have to do on the homework. What you would do here is you've got v of 1 right here, 2, 4. And that's at 1, right? So first thing you do is you find this point, right? That's the t equals 1 point, the 1, 3. 1, 3. After you do that, you need to plot this vector. You plot it starting here. So the vector is 2, 4. So from this point, you want to go 2 up, 2 over, 4 up. So like, where would that be? So, 1, 2 over, 1, 2, 3, 4 up. So this is the velocity vector at time 1, 2 over 4 up. And that looks correct, right? It's supposed to be in the direction of the curve. It's supposed to be tangent to the curve. So it looks like it is, right? So that's our v right there. Now the other vector that we can plot is the a of 1. A of 1 is 2 comma 0. You could also plot that right here. So it's 2 comma 0. So if you plot that vector, that's just 2 in the x direction, 0 in the y direction. So that's the a. It's the a of 1. And this was v of 1. Okay, so do you see what I was saying about how I plotted the velocity and acceleration vectors up here, right? So velocity points in the direction of the curve, right? If you think about this curve being in here. So velocity points in the direction of the curve. If it's turning, acceleration points in the direction to the inside of the turn. And that's what we have here, right? Velocity points in the direction of the curve. Acceleration points to the inside of the turn. If it's turning to the right, then it points to the right. Okay, so that's what we would do there. Now, as far as the homework goes, right, they give you the question like this. And what they say is the function r is shown as the red curve. And then they say drag the red point to select the value of the position at t equals 1, right? So what you would do is you calculate the things that I'm displaying right here, right? So you calculate these things, and then first thing you do is you find r of 1 is 1 comma 3. And then you have to drag this point to 1 comma 3, right? So you go like that, and now the red point you can see hopefully is at 1 comma 3. Then what you have to do is you have to plot the v and the a vectors. So you see that the v vector, which you calculated, is 2 comma 4. So that means from the red point, you need to go over 2 up 4. So here's the v vector I'm moving around. From here, you go 1, 2 to the right, 1, 2, 3, 4, up. And that's your v vector. Then you do the same thing for the acceleration vector. A of 1 is supposed to be 2 comma 0. So you take the acceleration vector here, and it's 2 comma 0. So from here, you go 2 to the right, and that's it. So it's really just the picture that I drew, right? But now I'm doing it on the graph. So the red was the r of t, and then the v was v, and the a was a. So you do those, and then you just hit submit, and it will tell me that I'm right. Okay, so that's kind of the first problem type, where you're going to be finding velocity and acceleration, and just making sure you can plot them on a graph, just like what you just did. Okay, so yeah, that's the basics of calculating that. Okay. Let me find a different problem. I see that they don't have a good one there. I want one like the homework again is what I'm looking for. Man, life is hard. Restart the homework. That's what I'm going to do. Preview. Well, you know what? Maybe we can just steal one from here. Next. Oh, next is never the right button. How many times have you guys done that? I do that all the time. You know what? It's going to take me too long. Okay. Okay, yeah, good. This is what I wanted. This is what I wanted. Okay, good. It gave me one right away. So here's another problem we can do with the same kind of stuff. So they say the position function of an object is given by R of t equals 3t squared, comma, 3t, comma, 4t squared minus 2t. And they tell us as well that t is in seconds. R is in feet. Okay, and what they want though, the question is, at what time is the speed at a minimum? Okay, that's what we want to know. Okay, and this is actually, this is a problem that looks easy, but it's actually more tedious than you think. You'll see when we go to solve this that there's more to it. Okay, um, so this is longer than you probably think. Okay, so this is longer than you probably think. Let's go ahead and try to do it. So if we're trying to find the minimum of the speed, of course, we should start out by finding the speed. So let's find speed. To start with. Okay, so we have r of t, which is 3-component vector here. We got 3t squared, 3t, 4t squared minus 2t. So far so good. Now speed comes from velocity. So first we find the velocity, which is the derivative of this function. That's going to be easy, of course. This is power rule, power rule, power rule. So derivative of 3t squared is 6t. Derivative of 3t is 3. The derivative of 4t squared is 8t. And then we got minus 2 for the other part. So there we go. Okay. Now, if it was just like velocity that we were dealing with, that would be one thing. But what we've got to do is we've got to get speed. So in order to get speed, we need to, the magnitude of this vector. So speed is the magnitude of this vector. So it's got that square root in there, and that sucks. So v of t, no vector symbol, is the magnitude of v of t with the vector symbol. And that's going to be the square root of 6t squared plus 3 squared plus 8t minus 2 squared, right? All of that. And so you do this, you get 36t squared plus 9 plus, what do we have? 64t squared minus 32t plus 4, I think. Let's try to work this out here. Keep going. So we got 36t squared, 64t squared. That's 100t squared. And then we got 9. Oh no, we got a minus 32t, I guess. Do we? I guess we do. Minus 32t. And then we got a plus 9 plus 4. So plus 13, I guess. Is that right? Let's suppose that it is. Is it? Let me just check. Okay. So, how should I say this? So there's kind of a trick here. Yeah. Oh, I just noticed, by the way, that when the book did this, they just didn't multiply this out. They just left it like that and said, oh, that's fine. That's kind of funny. But, we multiplied it out, I guess. Hopefully we're right, because if not, we're going to make a mistake now. Now, so we have the speed here. Okay, so this is speed. Speed equals little v of t. Okay, now once we have the speed, we actually have to find the minimum speed, right? Or actually, they didn't ask for the minimum speed. They asked for the time where speed was minimum. Okay. So find the time where speed is minimum. Okay. Now here's a trick. The book does not do this trick, but we should because this is going to save us a lot of work. Okay. So speed is right here. So technically what we have to do is we have to find the minimum of this function. We should find the t to minimize this function v of t, which is square root 100t squared minus 32t plus 13. That would involve finding the derivative and setting it equal to 0 and so on, right? You know the process for finding the minimum or the maximum of a function. This involves finding the derivative, set equal to 0 to get critical points, and then figuring out if one of them is the minimum or not. And that's quite a bit of work, right? Finding the derivative and so on. Because of the square root and stuff, that's what makes it a little bit tricky. But there is kind of a trick. And so the trick is this. So trick. Let's see. The t that minimizes, let's say, a square root of some function, also minimizes just the function inside of the square root. And what that means is that basically you can just throw out this square root symbol if you want to in order to solve this problem easier. You can minimize, that says minimize. You can minimize this one. So I'm just going to say like, I need to give it a different name here. Maybe I'll call it, I shouldn't call it S. I don't know what to call it. Speed. It's not speed. I'm just going to write it without the square root. 100 t squared minus 32t plus 13 instead of square root of 100t squared minus 32t plus 13. You can just not use the square root. Okay, so that's what we'll do. So I'm just going to say like minimize this. So now we find the minimum, the t to minimize. I still haven't given it a name. What should I call it? Just, I guess I'll call it, I don't want to call it S. I'm calling it S. It's not really S. But anyway, 100 t squared minus 32t plus 13. Okay, so no square root. So if you were going to try to find the minimum of this function, actually, I can't do it. I'm calling it g. Okay, so if you're trying to find the minimum of this function, what you do is, number one, find critical points by setting the derivative equal to 0. So you have to remember this from Calculus 1. All right, so find the derivative first, which is 200t minus 32. And that's a lot easier than dealing with the square root. Notice, set equal to 0. 0 equals 200t minus 32. So 32 equals 200t. So t is 32 over 200, which can probably be simplified. So we have 16 over 100. 4 goes into both of those. 4 goes into 16 4 times. 4 goes into 125 times. So we get that. Okay. Now, technically, we don't know if it's a minimum or a maximum. So you should do something to figure that out, if it's a minimum or a maximum. Test t equals 4 over 25 somehow to see if it's a minimum or maximum. And you can use the first derivative test or the second derivative test. I'm going to use the first derivative test. So what you got is you got t equals 4 over 25, which, can you grab a calculator? We can figure out how, I guess actually I don't need to. And at that place, g, remember g was just a made up name for the function. At that place, g prime was equal to 0, right? And so what you do is we're just looking at g prime here, which was, what was it? 200t minus 32. And just put in a point to the left of 4 over 25 and a point to the right. So test a point to the left and right of 200t minus 32. Oh, that doesn't make sense. To the left and right of 4 over 25 to find the sign of the derivative. Okay, so to the left of 4 over 25, we can probably just use like t equals 0, right? You usually don't mark that on your number line, but so put in 0. So if you put a 0 into this function, what do we get? We get 200, 0 minus 32, right? Which is minus 32. So that's negative. So this is g prime less than 0 over here. And then if you test a point greater than 4 over 25, 4 over 25 is very small, right? So less than 1. So I can put in a 1. That would be to the right of 4 over 25. Put that into the function, 201 minus 32. So that's just 200 minus 32. The point there is that that's definitely positive. Okay. So over here, g prime is positive. And so if you think about what you know about sign of derivatives, what that's telling you is that this function goes down, right, because of the negative derivative. And then here it goes up because of the positive derivative. So if the function goes down in this part and then goes up, then clearly right here there is a minimum. So at 4 over 25, there is a minimum, and that's the first derivative test, is what we just did. So we see that g has a minimum at t equals 4 over 25 by the first derivative test. And I'll show you how to do the second derivative test if you do the problem on Newton Alta. Okay, so we did it. So technically all this work that we did here where we were testing, like everything after this point was just to test if it was a minimum or a maximum. If you just did this, got this number, and then typed that into the computer, you would have gotten it right. So, you know, you would have gotten it right. So anyway, I wanted to do one of those because it's longer than it seems, like I said, and we did, so good for us. Okay. What else do we have in here? We've got, okay, I think we need to get to tangential and normal components of acceleration. Okay, so this is going to take a little bit of work. Tangential, not gentle, tangential, and normal components of acceleration. Okay, so in order to do these, first of all, before we kind of get into them, what I want to do is I have to go back to the previous section and just remind ourselves of a couple of formulas from the previous section here. Where is it? Yeah. Okay. So there's, I believe, what we call the unit normal t here. Yeah. Okay. So given r of t, a vector valued function, what we call the principal principal unit tangent vector is the t of t. We used that before, and it was r prime of t over magnitude of r prime of t. Okay, so we're going to be using this. So that's called the principal unit tangent vector. We are going to need one more thing, which is a little bit further on like, I think, curvature. So in section 3.3, we did a little bit of curvature, I think. And I don't think I did this, but yeah, I didn't do this. So I didn't do this part of section 3.3 because we didn't need it, but now we do. So there's a thing called the normal vector, the principal unit normal vector for a curve. And that one is defined to be t prime of t over magnitude of t prime. Okay. All right. So, I mean, I'm not really going to explain them too much here. We'll see what they do when we try some examples. But you need to have these definitions down in order to actually solve these problems in section 3.4. So having said that, now let's go back to 3.4. Where is it? Okay, there it is. Okay, so now we can talk about those things. Okay, there we go. So here's a picture now. So let's picture, again, a car like driving on the road, or in my case, probably a dumb looking skateboard driving along a road. Window. Okay. So let's just say that it's like just moving along a curve. Okay. And, we're going this way along the curve. Now, a couple things that we know. So there is a velocity curve on here, right? And we know that the velocity vector, and the velocity vector points in the direction that the car is traveling. So that's the v vector. Okay, we know that. And also, we know that there's an acceleration vector, right? Because we did that as well. So we've got an acceleration vector, which is somewhere in here, kind of points to the inside of the turn, and that's the acceleration vector. Okay, now basically what we're going to do is, if you take this acceleration vector and you project it onto v, so you take this and we go 90 degrees here, like that, and we get this vector, right? We have a name for that, right? That would be the vector projection of acceleration onto the velocity, right? Um, and what they do is they give that a name. They call that, what do they call that? They call that, where is it? Tangential component of acceleration. And so specifically that's going to be A sub t. Okay, and wait. Yeah, no, that's right. Okay, yeah. And then there's another one though, where if you take this length here and go out this way, I mean, you could do it right there, but if you go out this way, like that, then this would be the normal component of acceleration. And so the idea there is that, let me just put like a dotted line there. Okay. So basically what you're doing is you're taking this acceleration vector and you're breaking it up into two pieces. This piece is, in the same direction as velocity, obviously, which is the same direction as the tangent to the curve. That's why it's called tangential component of acceleration. And this one right here is, 90 degrees away from this one. But the point is that if you added AT and N together, it would give you the A vector. So that's why they're called tangential and normal components of acceleration. They're the components because if you added them together, you would get this. Okay, so that's what they are on the graph. And, what we would do is calculate them this way. So, is calculate them this way. So here they are. So let R of t be a vector valued function. So the same, definition that we've been using, that represents position at a time t. Okay. Then what we've got is the tangential component of acceleration is this. So that's the A of t that we saw. And it is, they just say A, the acceleration vector, dot with the unit tangent vector. Right, so that's why we have that. And then also, you could calculate it as they say, v dot a over magnitude v. And so the reason this works, wait. Okay. Yeah, so this is actually slightly bad notation. So they did this and then I copied them and now I regret it. But so if you take a look at this, the way this is defined, this is a dot product. So the result is a scalar. This is a dot product. So the result is a scalar. So this is a scalar. This is a scalar. So this is a scalar, right? Now on the picture here, they drew them like they're vectors. But essentially what we're doing is the scalar projection apparently, and you would have to get the direction itself from the v. V would give you the direction and A of t would give you the magnitude, which is, bad, but you'll see. So this is a scalar quantity, even though they drew it as a vector in the picture. Okay, so this is a scalar. I'm just gonna denote that scalar. Yeah. Scalar. Okay. And then the other one is an. And so that's just going to be vector a dot with the vector n, which again, that's why we listed this vector here, so we could calculate it if we need it. And another way to calculate that would be by magnitude of v cross a. They're just giving you other options for computing this over magnitude v. And they even give you a third way, which I'm not going to derive this, but they say magnitude of a squared minus the at, which you calculate first, squared. Okay, so this is, you know, this kind of quantity here would come from, you know, drawing a triangle here and using the Pythagorean theorem, basically, is where that would come from. Okay, the main thing here is that we know what they represent, right? We have a picture on the graph, this length and this length, and that's all they are is lengths, right? Even though I drew them as a vector here. So length, not vector, actually. Same thing here. This is a length, not a vector. Okay, despite being drawn as vector. So we find those two lengths. And if you actually wanted to write them as vector addition, so remember when I said that, you know, technically A was going to be AT plus AN? Well, not if they're scalars. So it wouldn't be AT and AN that you add up. It would be the vectors here that we drew, but they're not quite AT and AN. What they actually would be is as follows. So the acceleration vector, you don't add up AT and AN. What you have to do is you have to do AT, and then to get the direction, you would have to take the unit tangent. And then you have AN, that's the right length for the normal component of acceleration, but to get the length, or to get the direction of the normal component of acceleration, you need the unit normal. And so this actually makes sense when you think about it this way, right? Like, this is the tangent, unit tangent. So unit means it has length 1, right? So this is the tangent, and we're going to multiply it by this length. So like 3 times the unit tangent would give you a vector with length 3 in the direction of the tangent, right? So you get the length from this, but then use the this vector, which actually points in the same direction as v, to get the direction. And this one right here points in the straight out direction here, the unit normal, and it's unit normal. So if we multiply by this an that we're calculating, we would get the length that we want. So it's like a magnitude times something length 1, magnitude by something length 1. So it does make sense that they're doing that. And it makes sense that we're multiplying the tangential component by the unit tangent and the normal component by the unit normal. Right? Okay. So I said a lot about those, but let's actually just do some calculations, see if we can solve a problem. It's not as bad as it sounds, I don't think. I mean, I think I'm making it just too bad. Let me find a good homework problem, though. Maybe we'll just do one, since the homework just locked up on me. It won't load. No, it just loaded. Of course it did. Wait, what was... Oh, I don't know what I just saw. Okay, well, I'm just going to still a different problem here. All right. So that was... No, we need one that's like the homework. I can't give up, right? We're doing the homework. All right, so give me a second here. We're gonna find one. Maybe we'll find one here. That's what we'll do. Okay. Sorry about this. So let's cheat. Are we loading? Cheat. 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 Submit. Man, this is frustrating here. Load. Load, dummy. Are you freaking kidding me? Oh man. And it won't let me do the instructor sheet. Well, life is hard, guys. I don't know what to tell you. Okay, we'll go to the home. Okay, here's a problem. I could have just made one up. Okay, given r of t equals e to the t cosine t, comma, e to the t sine t, comma, e to the t. We're going to find the tangential and normal components of acceleration. Okay, so let's look at what we need to do this calculation. So in order to do AT, you either need to find the A vector and the unit tangent. The unit tangent, right, you can use this formula up here for r prime over magnitude r prime. Or you can use this formula, which is just using V and A. So actually this one just uses V and A. So I think this is going to be the easiest one to use, right? And then this one down here also uses V and A. So that one is probably going to be relatively easy to use. Now you could say like, oh, well, that one's got a cross product and this one doesn't. But this one would have the n in here, which, you know, you would have to calculate this, which would be the derivative of this one up here. And then you'd have to divide by its magnitude. And I feel like calculating this is more trouble than calculating a cross product, but it's up to you. The point that I'm trying to make is that you do have choices about which formulas that you use. Okay, I think I'm going to choose the ones that have the V and the A. Okay. So note that there were different forms for calculating the AT, the tangential component, and AN, the normal component. I'll just choose the ones that just use the A and the T vectors. A and V, instead of the ones using T and N. Okay, that's just going to be my preference here. So let's do this. So we got this RT. Okay. Well, we need R prime. So if we're going to take this derivative here, right, we've got R, we need the derivative here, but we're going to have to use the product rule, right? E to the t cosine t. So it's going to be a little bit tricky to calculate because product rule, but you're all in calculus 3, so product rule should not kill you. So like f prime g, f g prime. So e to the t, f prime g plus f g prime. So there's my product rule for the first one. Then for the second one, f prime g plus f g prime. That's for the second one, product rule. And for my third function, the derivative of e to the t is just e to the t. So let's write this out. This is e to the t cosine t minus e to the t sine t, e to the t sine t plus e to the t cos t, e to the t. All right. So that's R prime, which is also v of t, right? Okay. Now we also need the acceleration vector. So we need the A here. Now, you could also do this with the unit normal, but if you look at the unit normal, the unit normal here, the unit normal involves the derivative of the tangent, but the tangent involves the derivative of r. So this is really a second derivative as well. So it doesn't matter whether you write it in this form or, v and a, you're still finding the first and second derivatives. All right, so we need a of t, which is the derivative of the v of t. What am I doing? The v of t. And so that's going to be the derivative of this. That's going to be a lot more product rules and stuff. But it is what we have, so we have to do it. So we need the derivative of e to the t cos t. So that's e to the t cos t plus e to the t negative sine t again. But that's just for this. And then you have minus this derivative. So the derivative of e to the t sine t is e to the t sine t plus e to the t cos t. That's your first component. Your second component is going to be, pretty much the same thing here. I'm just going to write it on this second line. So your second component is going to be e to the t, e to the t sine t plus e to the t cos t. That's the derivative of this plus the derivative of e to the t cos t, which is e to the t cos t minus e to the t sine t. Okay, third component, the derivative of e to the t, which is just e to the t. So it's a little bit tedious because of the product rules, right? But let's see if we can clean this up. So in this first component here, you've got e to the t cos t, minus, right? So e to the t cos t minus e to the t cos t. That's going to cancel. And then here you've got e to the t, this is negative e to the t sine t minus e to the t sine t. So these are not going to cancel. These are going to combine, and you're going to get negative 2 e to the t sine t. All right, let's do the other one. Next one. So here you got e to the t sine t minus e to the t sine t. Those cancel. And then you got e to the t cos t plus e to the t cos t. So that's going to be 2 e to the t cos t. And then you got your last component, which is just e to the t. Okay, so that's not that bad, right? Like when you simplify it. So that's your acceleration vector. Okay, now once we have those, then we should be ready to actually calculate what we want. So we want the tangential component of acceleration. That's BAT. Which form are we using? We're using this one, V dot A over magnitude V. Okay, and yeah, it's going to be a little bit tedious to calculate, but we have what we have. So what's V? V is this thing, sadly. Let's hold on, stop. Duplicate. All right, so we have the V of t there. Barely have enough room to write it, which means let me just erase this and move this all over. Okay. All right, so that's your v to the t, that's your vt dot a. Where's your a? Your a is negative 2 e to the t sine t comma 2 e to the t cos d e to the d. All right, over the magnitude of v, but this is duplicate, put that there. So you have this. So what do we got to do? We got to do the dot product here. So in order to do the dot product means you have to multiply this thing by, right? You got to multiply this component by this component. You got to multiply this component by this component. And then you got to multiply your e to the t by the e to the t and add that all together. So you're going to have e to the t, like when you multiply this by this, let me just erase actually. When you multiply those together, you're going to end up with -2 e to the t squared, which is e to the 2t, and then you got a sine times a cosine. So sine t cos t. And then when you multiply this by this, you're going to get +2 e to the t looks like sine squared t when you multiply those. That should have been e to the 2t. Okay. Now we multiply the orange ones. So 2e to the t cos t, e to the t sine t. So that's going to be 2e to the t, 2e to the 2t, sine squared t again. And then when we multiply, oh no, not sine squared. I multiplied the wrong one. This is a cosine and this is a sine. So sine cosine, sine t cos t. And then when you multiply 2e to the t cos t times e to the t cos t, you're going to end up with 2e to the 2t cos squared t plus, and then you got e to the t times e to the t, which is e to the 2t. Ooh, bottom. Square root. Okay. What do we got to do? We got to square these. Oh man. So it's e to the, okay, you know what? Oh, I almost said a bad word, guys. You don't know how many lectures I've started over because I just started like swearing. You guys don't even know. All right. Squared plus squared plus. All right. So that's what you got to do in the denominator. In the numerator, let me see if we just notice anything like that we can do to cancel stuff out. Here's the main thing. Okay, here's what I noticed in the numerator, just looking. 2e to the 2t sine t cos t. -2e to the 2t sine t cos t. That looks like it cancels. If I didn't make a sign error, this and this just go away. All right. And then you've got these two things. 2e to the 2t sine squared, 2e to the 2t cosine squared, and then e to the 2t. So let me just write this. We got 2e to the 2t sine squared t plus 2e to the 2t cosine squared t plus e to the 2t. Everything's got an e to the 2t, by the way. Well, we're going to use that in a minute, but not yet. Now in the denominator there, we're going to have to FOIL all this out. All right, so we got to multiply this all out, all this out. So square that. So we're going to have to like square the first terms. So that's going to be e to the 2t cosine squared t, and then minus 2 e to the 2t sine t cos t, and then plus e to the 2t sine squared t plus, then we got to do the same thing here. This, everything's going to be the same, except this is going to be a plus sign this time, right? Because there's no negatives at all. Yeah, that's right. So I'm just going to actually cheat. Take this, duplicate it. Not that much. Try again. Take this, duplicate it, put it here. Did I really don't have enough room? Okay. Difference is this should be a plus. Okay. All right. Last thing is e to the 2t. Okay, let's see if there's any canceling to be done in the denominator. So let's see, e to the 2t cos squared, e to the 2t sine squared. Okay, those are going to stick around, I think. We've got a negative term here, right? 2e to the 2t sine t cos t, positive 2e to the 2t sine t cos t. Those are definitely going to cancel. So cancel. Then I've got this and this are positive. That's positive. That's positive. All right, so nothing else is going to cancel. All right, so here's what I want to do. In the numerator, oops, why am I writing a square root? In the numerator, everything has an e to the 2t, right? I'm going to factor out e to the 2t. If I do, then what I'm going to be left with here, take away the e to the 2t, you're going to have 2 sine squared t plus 2 cosine squared t plus, and we factored out e to the 2t, so just plus 1. Okay. In the denominator, what do we got going on? I've got e to the t cos squared, e to the 2t cos squared, same term. So that's 2e to the 2t cosine squared. I don't know what happened there. Cosine squared t. Then I've got the same thing for sine, so 2e to the 2t sine squared t. And then finally I've got e to the 2t. Okay, now I can also do the same thing there. So let me just e to the 2t, 2 sine squared t plus 2 cosine squared t plus 1. I know this is really long and tedious, but like, trust me, we're going through it for a reason here. In the denominator, square root, I can also factor out an e to the 2t, and I'll be left with e to the 2t. Okay, sine squared t plus e to the 2t. That should be a 2 and a 2 again, right? 2. Cosine squared t plus 1, right? So that's just like the same thing, but on the bottom it's in the square root. Okay, that's fine. But anyway, here's a punchline. Well, not yet, but here's the thing that you know, right? Remember, oh, I wrote the denominator wrong. Let me fix the denominator real quick. Right, in the denominator, the point was that I was going to factor out an e to the 2t. So if you factor out an e to the 2t, then you're going to have actually just 2 cosine squared t plus 2 sine squared t plus 1. Okay, right, same thing really in the numerator and the denominator, just the denominator has a square root, extra square root. But here's the thing I want. We've done this a couple times before, right? What's cosine squared theta plus sine squared theta, right? That's 1. And if you've got 2's in front of them, like these two do, then that would just be, right, 2 cosine squared theta plus 2 sine squared theta, sine squared theta. That would just be 2. So actually, what you've got going on here is that this is just 2, and this is just 2. So when you work this out here, we're actually going to get on the top, we simply have e to the 2t, and then in those parentheses, we just have 2 plus 1, literally just 3 there. And in the denominator, basically the same thing. You've got e to the 2t, and then this is 2 plus 1, which is 3. Okay? Now, as far as dealing with this, we've got e to the 2t, 3e to the 2t. On the denominator, the square root of 3 is square root 3, and the square root, and the square root of e to the 2t is just e to the t. So you have this. And then 3 over the square root of 3 is square root 3. And e to the 2t over e to the t, you subtract the exponent, so 2t minus t is 1t. So that is actually my answer. So we did all of that work, right? And it actually comes down to AT is square root 3 e to the t. Crazy, right? All that work. Look how big that was. It was so hard to even fit it on the page. It was so expansive. Okay. So I wanted to go through that just to show you that it's tedious, but also, you can do it. It's not impossible. Now, it would have been easier just probably to type this. You can type this into like Wolfram Alpha to like check your work, that kind of thing. I'm not going to do it all, but like you can go Wolfram Alpha, right? And remember, you can just start typing this in, right? E to the t. You get to use copy paste if you do this. Cosine t minus e to the t sine t, right? Like you can type this whole vector in. I'm not going to do it, but like, you type in your whole vector. It's not this, it's not this, but like you type in your whole vectors with all the e to the t's and everything else. Like even maybe I'll do this actually. I'll put in a vector. This is obviously not yours, but this one I can type in without taking too long, right? So those are two vectors that I just typed in. And, back at the beginning, right, you can say like dot, and then you type in your two vectors with a comma between them, and it will know what you want. And it doesn't care. Equals. Are you loading? Load. Are you loading? Load. 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 It just won't go. Thanks, Wolfram. Really? Oh, you finally did it. Okay. The point that I'm trying to make here is that Wolfram Alpha can do dot products even when you put functions of t inside of them. Okay? So there you go. And I'm not sure, like maybe the way that they represented the dot product, I wonder if this works. Hold on, checking something. So if you don't want to type dot, I wonder if dot, like the period dot, will do a dot product. Yeah. So like that dot that you can see there, but come on, over here. This dot is a period. So you can do a dot product that way. So if you wanted to check like the dot product in the numerator and you want like the simplified version of it, you could have just actually typed in that entire numerator there, the yellow, orange, and green there, and make it do the dot product, and it would have done all the simplification and hopefully would have gotten you down to 3e to the 2t in the numerator. Now, I'm not saying, cheat on your homework or anything, but I am saying you can check your answers and, see what kind of answer you're supposed to have and that kind of stuff. Okay, we did AT. We didn't do the other one. We still have to do the other one. So what do we want to do? So our choices are a cross product between V and A. I don't like that because V is long. Our second choice is to use this formula, which uses the magnitude of the acceleration vector and also the AT. Now the AT we know is pretty small, so this looks like it's going to be a better form for us. So I like this one, right? But I'm thinking about it. Do we want to do this? Do we want to do this? Do we want to do this for calculating AN? And this looks the easiest, but stop and think. Is it the easiest before you pick one? Okay, so I'm just writing that there. So the next thing is we still need to calculate AN. Oh, no, don't erase it. Why did I erase it? Okay, we still need the normal component of acceleration. And so for this one, this formula looks the easiest to me on this problem. And just to explain why I think that, here's why I think that. This is AT. AT turned out simple. So this is not going to be complicated. This is the magnitude of A. And if you look at A itself was pretty simple compared to like V, right? So I was trying to avoid V, and I would rather use A. So when I'm looking at these formulas here, I see all these V's, I don't want to deal with V. Here I see no V's, and I see A and AT, and those look, I know that those formulas are a little bit shorter. So that's why I'm choosing it, right? Just length of the function, so I can save some writing here. So that's why I think it looks the easiest. So we have to compute this. We know AT, we need the magnitude of A. So we have AT from the previous part. Root 3 e to the t. Hopefully I did that right. If I made a mistake, then this is going to be wrong. We still need magnitude of the A vector, right? That's the A vector. Okay, so what's the magnitude of A vector? Well, I mean, that's not that hard. Oops. The A vector, let's find it. Here it is. Right? Not super long, because we simplified all those product rules and they just managed to go away. All right, so we need that. So that doesn't look too bad. So that's going to be a square root. Square this. It's going to be 4 e to the 2t sine squared t plus square this. 4 e to the 2t cosine squared t. Square this. That's e to the 2t. Not so bad at all, right? Because we know this looks familiar. We just dealt with something like this recently. I know I can factor out the e to the 2t and have 4 sine squared t plus 4 cosine squared t plus 1. Four sine squared plus 4 cosine squared, that's 4. 4 plus 1 is 5. This is this. And square root 5 is square root 5. And actually, we're going to square this anyway, right? So we may as well just leave it this way. So let's actually just leave it like that. Let's just say square root 5e to the 2t. And that's perfectly fine. Okay? So what do we want then? So now we're going to use our an, which was the square root magnitude of a squared, right? Plus or minus at squared. All right, so we just fill them in. So an is, oops. Come on, right words. Okay, magnitude of A. So the magnitude of A is what we just calculated. That's that 5 e to the 2t squared minus at squared. At was somewhere here, square root 3 e to the t squared. So we have that. So an is square these. So if you square this one, it's just going to cancel out that square root. You're going to get 5e to the 2t. If you square this one, you've got square root of 3 squared. It's going to be 3. And e to the t squared is e to the 2t. So 5e to the 2t minus 3e to the 2t is 2e to the 2t, which is square root 2 e to the t. All right. So we did it. So what we ended up with was, for the final answer, we had AN was root 3 e to the t. AT, I got that backwards. AT was root 3 e to the t. And AN is what we just calculated, is root 2 e to the t. That's the tangential component. And this is the normal component. And that's what they asked for. And the whole point was that, in theory, the acceleration vector is the AT times the t vector plus the AN times the n vector. And so the AT was root 3 e to the t. T plus root 2 e to the t n. Now, we didn't actually calculate the t and the n because we didn't need them. We didn't need to calculate t and n in order to calculate this. So we calculated this without the t and the n. But okay. So that's the tangential and normal component of acceleration. They're long. You got to do a couple of them. Check your dot products on Wolfram Alpha if you have to. Check your product rules if they come up. Not every problem has a product rule. This one did because, it was just a book problem that I picked out. And yeah, best of luck to you.